This is Dr. Sandeep, Associate Professor in the Department of Mechanical Engineering, working in Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about the ceramics and its classifications and applications. In the previous sessions, we have discussed about the ferrous and non-ferrous materials. So in ferrous materials and non-ferrous materials, we have seen the structures of each type of ferrous as well as non-ferrous materials. And also we have discussed about the applications of the ferrous and non-ferrous materials. Now, apart from these ferrous and non-ferrous materials, we have different types of other materials. So these materials comes under the engineering materials fourth category of engineering materials will come under the ceramics, polymers and the composite materials. So we'll try to understand what is the applications of the ceramics, where we can apply these ceramics, where these ceramics have been useful, and what is the microstructure of these ceramics, and what is the composition, different types of composition ceramics we'll study in this session. Now, ceramics are compounds between metal and non-metallic elements. So, generally, in the iron carbide phase diagram, what we have seen that the carbon is changing from iron is changing from carbon, and this carbon is changing from graphite. So, during this transformation, during the phase transformation, what we are having, we are getting the different types of elements depending upon the composition as well as the temperature. Now, in those phase transformations, we are getting the metallic and non-metallic elements. So, which is having iron content, which is not having iron content. So, with the description of the iron content, we are trying to classify whether the material is ferrous or non-ferrous material. Now, coming to the ceramics, what is happening here? The ceramic compounds are between the metallic and non-metallic elements. This we have to identify. So, wherever we find the elements or compounds in between the metallic and non-metallic elements, those type of elements are called the ceramics. And they are most frequently of oxides, nitrides and carbides. So, we have to identify that. What is happening? The main thing is the materials which are in between the metallic and non-metallic elements are called as ceramics, and most of the elements we frequently call it as oxides, nitrides and carbides. If we found these type of elements, these comes under the category of ceramics. So what is happening in this case? If you consider some examples of the common ceramic materials, so we have the aluminum oxide, silicon dioxide, silicon carbide, silicon nitride, and in addition, what we can refer to the traditional ceramic materials, which is composed of clay. So generally, we'll have an idea of ceramics means the clay what we are using in the olden days. So with the help of these clay, what we are trying to use, we are trying to produce the porcelain type of materials. So we have seen the porcelain type of materials. So generally, basic knowledge of ceramics describes in the previous earlier days we used to perform the manufacturing of using the clay material, the ceramics. Okay, that refers to the ceramics, as well as the cement and glass. So this also comes under the category of ceramics. So mostly what are the oxides, nitrides or carbides? These we are observing. So these comes under the category of ceramics. And in the previous olden days, we used to perform any manufacturing of the porcelain type of materials. So that also comes under the ceramics, as well as the glass and cement. So these are also some of the examples, common examples what we are using daily life. Okay, these comes under the ceramics. Now, with regard to mechanical behavior, or ceramic materials are very stiff and strong. So in order to enhance the mechanical properties, what we are trying to do, we are trying to add something into the ceramic materials to enhance or to improve the mechanical properties of the ceramics. Okay, so like that, that's why we are trying to use some oxides, nitrates or carbides into the ceramic materials to improve the mechanical properties. So any type of material, if it is a single material, it is having some different properties. Now, if you add some another alloy into that, what is happening? It is trying to enhance the mechanical properties or the chemical properties. Now, if you compare the single material with the already some addition of other elements, so what is happening here? There is a lot of difference. There is a lot of difference between the two materials. Suppose if you consider A and B. Now, A metal is composed of a single material, that is some oxide. But in this case, the B material will oxides plus nitrides. That means you are trying to add some other material into this. So what is happening here? There is a lot of increase in the properties. So properties again related to mechanical, chemical. So like that, you're trying to enhance the properties by adding some other element into the original element. Now, if you compare these two materials, so B is having some different type of properties when you compare with the A material. That's why there should be some addition of any other elements into the base elements to improve the properties of different types, whether it is a mechanical or chemical. So like that, you have to identify what type of material we are trying to use depending upon our application. Now, this ceramics comes under the metallic and non-metallic. So wherever you find the materials or the elements in between these two categories, then that type of materials are called the ceramics, and most frequently used ceramics are called the nitrates, oxides and carbides. Okay, so these we have to remember. And the most common day-to-day life examples what we are trying to use is that glass, cement and the porcelain type of materials. So these are also comes under your ceramics categories. Now, where does this ceramic term came from? So this ceramic from the Greek word keramikos. Keramikos is the Greek word which describes the ceramics. So keramikos means stuff, burn stuff. That means you're trying to burn the material. So whatever the material we're trying to manufacture, what we have to do, first of all, we have to do the heat treatment process. So once you do the heat treatment process, then only it becomes a solid type of material. So whatever the clay material we are having, so directly we can't use this clay material for any purpose. So once you heat this, once you make into some model, with different dimensions, after if you do the heat treatment process or the burning process, that is called burn stuff. Keramikos is nothing but the burn stuff. Once you burn the clay to the required temperature, then you can use for its utilization. So like that, this keramikos is nothing but the burn stuff. This indicates, what does it indicate? Means it indicates desirable properties of these materials are normally achieved to the high temperatures. So what are the temperature, temperature to the different materials? These can be done once you do the heat treatment process, then we can achieve the mechanical properties. Okay, to get the desirable properties, whatever the desirable properties is required or required for the application can be obtained by heating the material. That's why it is called as a burn stuff. So whatever the properties are required to our applications can be achieved by burning the material to the required temperature. So we'll get the desired properties. So this means the keramikos in the Greek term, that is called the burnt stuff. And now if you go to the classifications, different types of classifications are there based upon the atomic structure. So how can you define the ceramics? So first category comes under the atomic structure, based upon the atomic structure, whether it is a crystalline or non-crystalline ceramics. So based upon these two categories, we can classify one of the classifications of the ceramics. And also this can also classify into three different categories based upon the materials. So first one is the based upon the atomic structure. We are trying to classify into two, and based upon the material categories, again it is being divided into three categories, that is oxides, non-oxides and composites. So first of all, if you see the structure, atomic structure, if the atomic structure is a crystalline type of atomic structure, then that type of category comes under crystalline. And of course, if it is non-crystalline, that is the another category of ceramics. And coming to the material categories, different types of materials which are present in the ceramics, again based upon those presence of the materials, again these ceramics have been classified. First one is oxides. So if there are high percentage of oxides present in the ceramics, then that category comes under these oxides, and there is no 0% of oxides present in the ceramics, then that type of classification comes under the non-oxides. And last one is the composite. So different types of materials which are being clubbed and seen as a single element, then that type of ceramics comes under the third classification, that is the composite. So based upon the type of atomic structure, based upon the type of material which is available in the ceramics, so like this we are trying to classify the types of ceramics. Now if you see the properties, again depending upon the type of ceramics, so we have discussed in the previous slides, based upon the structure and based upon the material availability, the ceramics have been classified. Now depending upon these classifications, again the properties vary, each property vary, is it not? So like that, first of all, if you see the brittle fracture of the ceramics, so what is happening here, at room temperature both crystalline and non-crystalline ceramics almost always fracture before the plastic deformation. So what is a plastic deformation means? So once you apply a load on the body, once you apply some load on the body, what is happening? It deforms. So if it deforms and continuously if you apply it, what is happening? The deformation will turn into fracture. That means the material will break. So if the material is not regaining its shape though you remove the force, that type of material is called elasticity. But in this case, plastic deformation is what? Though you apply the force and remove, so what is happening? It is continuously deforming. So that is the difference you have to identify. So first one is what? I'm trying to apply a load on the body. After some time, I remove the load. What is happening? Whatever the body is there, that is again coming back to its original shape. So just consider an example of a rubber band. So this is an elastic deformation. Okay. So once you apply a load on the body and remove the load, what is happening? It is regaining its original shape. That type of transformation is called as elastic deformation. Now in this case, the crystalline materials at room temperatures, what is happening? It is turning to deformation, plastic deformation. So what is this plastic deformation? Though you apply load and remove, so what is happening? It is not regaining its original shape. It is completely deforming. It is not coming to its original shape back. It is getting deformed. So that type of point where the material is getting deformed after removing the force also is called as a plastic deformation. So in this case, what is happening? At room temperature, both the crystalline as well as the non-crystalline ceramics almost always fracture before the plastic deformation. That means these type of crystalline and non-crystalline type of ceramics are being fractured. That means they are getting brittle in nature, very, very brittle. So they are getting fracture before the deformation only. So any material in general, if you consider, after plastic deformation only, it will break, it will get fractured. But in this case, the ceramics, what is happening in this case? Ceramics, whether it is a crystalline or non-crystalline, it is getting fractured before the plastic deformation. That means in between the elastic and plastic deformation, the ceramics are being fractured at room temperature. So this is very important point you have to note down. That means how it is being fracturing before the plastic deformation, that can occur in response to the applied tensile load. So again, what type of load you are giving, whether it is a compressive or tensile load. So tensile load, that means you are pulling the body from the both ends, the opposite direction. That is called the tensile load. So now what we are trying to do here, we are trying to give some tensile load on the ceramic materials, whether it is a crystalline or non-crystalline material. At normal room temperature conditions, the ceramic materials are getting fractured before the plastic deformation under tensile load. So this is very, very specific. So depending upon these mechanical properties or the behavior of the material of the ceramics, we are trying to use to the required application. So like that, you have to identify what type of deformations or what type of mechanical properties are being varied depending upon the type of load or depending upon the type of material. Okay, once you understand all these things, then it is very easy for us to identify the exact material to the application. So this is one of the brittle fracture of the ceramics, how it is happening during the tensile load application, whether it is a crystalline or non-crystalline type of ceramic material. Now, the brittle process consists of the formation of propagation of cracks to the cross section of the material in the direction perpendicular to the applied load. Now, where you are getting the exact the brittleness of the brittleness to the material. So, wherever you apply the load on the material, exactly at that point only the material starts deforming. That means it is getting brittle in nature. So, exactly at the point of application of the load, exactly at the point of application of the load and perpendicular to the load where you are applying, at that point only it is getting brittle in nature. So that point you have to identify when you are applying a load on the material. Exactly at the point of load perpendicular to the load, the brittleness of the material is getting achieved. Now, crack growth in crystalline materials may be either transgranular or intergranular. So, depending upon the granulars inside the material, okay, how the deformation is being taken place when you apply any load. So, that also describes whether it is a transgranular or intergranular. And also the fracture or cracks, whatever the forming inside the material, okay, it specify the crystallographic or which type of phase it is being transformed. Now, if you want to find out what is the maximum point up to which this brittleness of the material can withstand, we want to calculate. So, the measure of ceramics material to ability to find out the resistance of the material to get fractured. That means any material when you apply the load, it gets some fracture in nature. So at what point, at what maximum point this can resist? So my body can resist the brittleness up to what point? Similarly, the ceramic materials at what point, up to what point they can resist these fracture or brittleness can be calculated with this formula. So when crack is present in a specified term, okay, that is the fracture toughness. So fracture toughness is the ability, okay, to overcome its fracture though you applied the load. So in order to calculate that, what is happening, KIC is called the fracture toughness. That is how much load it can resist, up to what load it can resist can be given by KIC, and this is given by Y sigma under root of pi a. So here Y is the dimensionless parameter or function that depends upon both the specimen and the crack geometry. Now when you applied load, what is happening here, it is getting brittle in nature. So some cracks will form on the material. So these cracks may have different types of geometry, whether it can be linearly or some circular or different types of geometry. So that's why it is a non-dimensionless parameter, this Y. What are the Y you are seeing here? That is a non-dimensional parameter that depends upon the type of geometry of the crack. And sigma is the applied load. So what are the load you are applying, the stress you are applying on the material. So that describes the sigma. And A is the length of the surface crack. So at how much length or how much length of the crack is being covered, that gives the A here. So this is how you have to calculate what is the, how to measure the ceramics material ability to resist from the crack formation. Okay, that is given by KIC, how much it is being resist through the load of the ceramics, and Y is nothing but the dimensions for value which depends upon the type of geometry of the crack, and sigma is a load which we are applying on the material, and of course A is the length at what, up to what distance the crack is being formed, that is given by A. So these are all the parameters which are included in order to find out the maximum point up to which the body can resist from formation of crack. So this is how, these are some of the different types of brittleness of the materials. Now if you see the first figure, impact or point load. So this is the point load what we are giving here exactly at this point. So if we give load exactly at the center point, so depending upon that load, what is happening, these cracks are being distributed along all the directions. So these are all the cracks which are being forming on the material. So these are different. So in this case, so what are the formula we have here? y sigma under root of pi a. Y sigma under root of pi a. This is the formula what you have. So here y is the dimensionless. That means what type of geometry you are having. So here you can take it as a linear example here, linear type of geometry. And here the point load, what are the load you are applying here? This is called the point load sigma. Pi, of course, you can take it as 22/7 or 3.14. A is the length. So this length, how much length of the crack is being formed. So this is the length of the crack. So like this, you have to identify different types of material depending upon the type of load, how these cracks are being formed, and what type of geometry is the crack formation, and what is the length of the crack formation during the point load. So first example describes the point load. This is about the point load. Now coming to the second figure, it is about bending. So when you bend any ceramic material, so what type of cracks are being formed can be identified here. So once you want to bend this material, so like this type of formation of brittleness in the material. So when you compare the point load with the bending load, different types of cross section of these brittleness in the material can be observed. So like that type of load varies the length of the brittleness, length of the dimensions, and how the load are applying, how the geometry of the brittleness also again observe different types. Now coming to the torsional, the third category comes under the torsional. So if you see here, when you rotate the material continuously, that is the torsion type, and again load you are giving. So depending upon the torsional, you are getting these type of brittleness in the material. Similarly, if you are giving a high internal pressure, that means if you are giving a lot of load inside the body, then again internal pressure is created. So because of the internal pressure inside the body, what is happening? So you can observe all these red lines. So these are all the different types of cracks which are being formed internally. So like that, depending upon the type of load, so though it is the same material, but the type of load describes the type of failure in the material, and also type of load describes the type of geometry of the crack formation. Also type of load describes the length of the crack formation of the material. So for the same material, we are getting the n number of things when you are applying load, type of load you are giving, or any bending type, torsional type, or internal pressure for the same material. So like this, there are n number of categories of the failure of the material. So this is one of the example to describe the different types of loads when you apply on the ceramics, what types of cracks are being formed, and what type of what is the length of the each crack, and what type of geometry of the failure we can observe by taking this an example. Now like in this example, if you consider, there are different types of mechanical properties based upon the composition. So in the earlier slides, we have discussed about the classification of the ceramics based upon the type of atomic structure, and the second category is based upon the type of elements which are being available inside the body. Okay, so the atomic structure, based upon the atomic structure, we have seen how the material is being failured or being deformed before the plastic deformation when you are applying a load, tensile load at the room temperature we have discussed. Now the second category is what? Depending upon the type of material or type of composition, the mechanical properties are being varied. Now if you consider the first example here you have silicon nitrate. If it is a composition of silicon nitrate, then the flexural strength, that is the strength up to what point it can resist, is given by, from minimum is to 250 megapascals, the maximum value is 1000 megapascals. Similarly, modulus of elasticity, that means we have discussed about the elasticity property of the material, up to what point it can resist. After this elasticity, it again converts to plastic deformation. That plastic deformation is nothing but the failure of the material. So what is the maximum limit the material can be at up to the elastic limit? So that gives this value. So this is the 304 gigapascals. So when we consider any silicon nitride, then the flexural strength of that means the tensile strength is starting with 250 megapascals and ending with the 1000. So it is not more than 1000. And the modulus of elasticity is 304 gigapascal. Now, if any application if you are taking, if that material is undergoing some elastic property of 500 gigapascals, then you should not consider this silicon nitride. So that's why before selecting the material to any application, you have to know the properties of the materials. Once you know the properties of the material, then only you can select the material. So you should not select the material before and start doing the working process. No, it is not correct. First you have to know the properties, you have to study the properties. Then only after knowing all these properties, then you can apply the material to the application. So like that, in any example, if the material is undergoing a flexural strength more than 1000, then you should not again use this. Then you have to go with the next type of material, that is zirconia. Like that, you have to know the properties, you have to know the compositions. Depending upon all these things, then you have to select, yes, this material is suitable for this application. So that is how you have to select the material for the application. Now coming to the second one, zirconia, you have here 800 to 1500 megapascals of flexural strength and 205 gigapascals of modulus of elasticity. Now, if the material is undergoing a maximum value of modulus of elasticity of 200, then you can go with this thing. And again, if it is the flexural strength is more than 1000, then you have to go with this, like this. So in the previous case, if it is more than 1000, you should not use this silicon nitride, but you have to go with the zirconia. Why? Because it is having up to 1500 megapascals. But coming to the modulus of elasticity, it is up to 205 only. But I need about 300, then you have to go again with the silicon nitride. So these compositions are very, very important. Depending upon these compositions, the properties vary. If you are very small percentage of composition, there is a huge variation in the mechanical properties. Now coming to the other silicon carbide, here again it is coming to less values of 100 to 820 megapascals, and coming to the modulus of elasticity, we have 345 gigapascals. Again, it is getting slower and slower. Coming to aluminum oxide, you have 275 to 700 and 393 gigapascals of modulus of elasticity. So, like that. Coming to the glass, that is the ceramics, 247 megapascals, 120 gigapascals of modulus of elasticity. That's what. So, if you know this application, it is very, very easy for us to identify the exact material from all these things categories, and you can apply to the application. And coming to the other applications, what we have, they are used in space industry because of their low weight. So since these ceramics are very, very less dense materials, so what is happening, the weight is also very, very less. So because of this less in weight in nature, we are trying to use these type of materials in the space industries. So space industries require very light weight materials. So that's why these ceramics are being one of the examples where you can apply in the space industries because of the less weight. And also they are used as a cutting tool. So cutting tools should be very, very sharp, and they should have very long life. Okay, so that's why these ceramics can be used as a cutting tools in the manufacturing process. And also they are used in the refractory materials, and they are used as a thermal insulators also. So high temperature, when you do any experiments during the electrical things, they can be insulated. The ceramics can be insulated as insulators in the thermal related applications to avoid the heat. And also they are used as electrical insulators also, thermal as well as electrical. So both categories, these ceramics are being used as an insulators in these categories. And coming to the advantages, most of the ceramics have high hardness, hence they are used as a abrasive powder and cutting tools. So since you have wide applications of these ceramics, what is happening, the main thing is what, it is very hardness. These materials are having very hardness in nature. That's why these are used as an abrasive powder and the cutting tools in the most of the manufacturing industry, and they have high melting point. This is very important. So since it is having very high melting point, it can work up to high temperatures also. At high temperatures, if you want to do any manufacturing or cutting process, so that's why these ceramics are being used as a cutting tools. So since it is having high melting point, so that's why these metals are being used in the refractory materials, and they are very good insulators, and this is one of the other reason to use them as a refractory. So since it is having a wide applications like insulators, high melting point and high cutting tools, so you have a number of applications using these ceramics since it is having very high hardness in nature, and they are high electrical resistivity, which makes them suitable to used as an insulator. Why you are using these ceramics as insulators means they can resist to electricity, they can resist to thermal conductivity. So because of this resistance to the electricity as well as thermal properties, that's why these ceramics are being used as a insulators, and they have low mass density, which results in less weight components. So since it is having very less in dense, they can resist to electricity. So that's why these are being used as an insulators, and also because of the less weight in nature, so they are used in most of the applications where the low weight is required, like space industry, okay, aircraft engine, all those things. These type of ceramics can be used because of the less dense in the material. So if you have a high density, then you cannot use it in the space applications. So most of the space applications materials can be used with the help of the ceramics because of the less weight in nature, and also they are generally chemically inert, which makes them durable. So these are very long life materials since it is not chemically inert. Okay, when you expose the ceramics to any atmospheric type of different type of climatic conditions or any chemical reactives, generally it won't react. So that's why the durability of these ceramics is very long when you compare with any other material. So that's why the metallic and non-metallic materials, when you expose to different climatic conditions, what is happening? It is being corrosed. But once you do this, take the ceramics, and when you go compare with the metal and non-metallic materials, it is very durable. Why? Because though it is exposed to different climatic conditions, it is not being corrosed. That's why the ceramics are being found in between the metallic and non-metallic materials. So this you have to identify. So this is the advantage of the ceramic material, since it is having very long life and it is very durable when you compare with the metallic and non-metallic elements. Coming to the disadvantages, they are very brittle in nature. So once if you give a point load, so we have seen different types of failures in the different type of load when you apply. So since it is very brittle in nature, since small application of load, what is happening? There is a lot of brittleness in the material. So that's why this is one of the drawback, where the point load or any bending type of load or torsional load or pressure, a lot of pressure you are giving, so it is being exposed to brittleness in the nature. That's why try to avoid the brittleness for the material by taking care of all the properties. And they have almost zero ductility. So ductility is what? It won't elongate though you apply the load or when you give some heat. So that is one of the drawback. It can't bend to any shape. Once you prepare one shape, it is fixed to that shape only. Why? Because since it is having very brittleness in nature, you can't bend. Once you start doing the any bending process, ductility thing, so it will directly break into things. But once you compare the metallic and non-metallic materials, it is very ductile material. So this can easily bend to any type of shape, and you can do the working process. But the ceramics, once you prepare in one shape, it is fixed to the shape only. If you want to turn into other shape, it will completely break and collapse. That's why this is very zero ductility. This is one of the drawback for the ceramics. This is one of the disadvantages. And also they have very poor tensile strength. Poor tensile strength means when you apply a tensile load on the body, what is happening? It won't elongate. It won't elongate it, but suddenly it will break at some point. So that is one of the drawback. But some materials will have elongation process. So some need these tensile strengths. The high values of tensile strengths are required in any manufacturing process. That is one of the drawback in this case of ceramics. They show a wide range in the variation of strength even for the identical specimen. So very wide range of variations in the strength. So one metal will have different type of strength, another type of ceramics will have different types of strength. So because of this wideness of the variations in the strength of the metal, so these are identified as some specific applications only. They cannot be used as in wide applications. But when you compare with the metallic and non-metallic, they are wide applications. They have a number of applications. But in this case, since it is having very less applications because of the different types of variations in the strength, these cannot be used in a specific. These are only used in a specific applications only. They are very constrained to some application, and they are difficult to shape and machine. So since it is having very brittle nature, so manufacturing of different shapes and machining is very difficult for these ceramics. So this is about the ceramics, the classifications and what type of ceramics you have. So mainly the ceramics can be available in between metallic and non-metallic. That you have to identify. And mostly carbide, nitride, and silicon nitrates. All these things are the generally most ceramics what we are trying to use. And the day by day, the improvements in the ceramics can be classified into the composite materials also. And the ceramics are being classified based upon the atomic structure. So two categories we have, crystalline and non-crystalline. And these crystalline and non-crystallines are being deformed or being fractured before the plastic deformation when you are applying a tensile load at room temperature. That is one of the drawback what you have. So based upon that drawbacks, you have to identify the application. And what is the second category we have? We have based upon the materials which are being available. So that is the second category what we have. And coming to the mechanical properties, the brittleness of the metal is very high when you are applying different types of loads on the body. So since it is having very brittle in nature, you are having very limited applications using the ceramics. Once you prepare the ceramic into one single shape, you cannot alter the shape. So that's why the machining and shaping of the ceramics is very difficult when you compare with the metallic and non-metallic elements. Okay, so these are some of the references where you can find the ceramics related thing, the classifications and all the categories. So Introduction to Physical Metallurgy is one of the reference where you can study the ceramics classifications and what is the basics of ceramics. Next, Essential of Material Science and Engineering is another type of classifications you can identify. And Material Science and Metallurgy, there you can see all the different types of microstructures, what type of load when you apply, how the brittleness of the metal can be altered. All these things can be seen from this. And Material Science and Engineering, these are some of the basics books or the references books from you can identify the ceramics classifications and all the categories. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.